Hi all, welcome to next tutorial, that is basic menu to one abstract model. The objective of this tutorial is to understand more generic basic menu to one abstract model, force convection and its usage. In the last session of previous tutorial, we added an extra class rotate A along with the fluid class, which means we can add many classes to one component. This menu to one principle allows users to capture CAE knowledge in a generic way, compacts the abstract model itself, and make it reusable across geometries. Hence, idea of this exercise is to collect into one abstract model the ability to handle force convection CFD problems of all kinds. Most importantly, this abstract model you can use to start authoring any of your force convection CFD problem. You can use this model as a base and then as per your requirement add classes, relations and attributes or edit the attributes. Once you set up your workflow, then you only need to prepare properly tagged CAD models for production work. So have look at the representative schematic below. Note that this does not cover all the attributes in order to keep it simple. So we have like global and model class, then we have attached inlet 2D, outlet 2D and no BL wire 2D classes. Then we have the fluid class, air class, size A class, size B class, air underscore porous A and air underscore rotate A. So these are the different classes present in the AMF. So if we see the schematic of the relations and attributes, you can see that there is a relation between fluid and inlet underscore 2D. Similarly, there is a relation between fluid and outlet underscore 2D. So on this relation, we have attached no boundary layer attribute. Then we have set up or specified the inlet boundary condition, and we have specify or we can specify a monitor. Similarly, on fluid relation, we can specify non-physical boundary condition, and on this relation we have specified outlet boundary condition, and we have specified no boundary layers attribute to skip the boundary layers, and we have specified the monitor attribute. On boundary of fluid, we have specified the wall boundary condition. So similarly, similarly to fluid class, we have like air class or air underscore porous A class or air underscore rotate A class. So on these classes we specify element set boundary condition, and sometimes on walls of this air rotate A or boundary of air rotate A, we specify a rotating wall. So we have like size A class for mesh defining mesh sizing, and BL wire A class to specify or define the boundary layers. So on global or model class, we specify the initial condition, then some monitor, we create the general monitors, then we specify moving reference frame or material model, or related to meshing we specify mesh curvature or minimum curvature and length scale factors. So this is the generic schematic. So we have been provided with the geometric abstract model, basic menu to one, and set of three tagged CAD models, that is Y duct, Y tube and MRF. For this exercise, have a look at our product description and schematic of our abstract model below. So this is Y duct model. So there is one inlet and two outlets, and there are four parts on which we are going to specify fluid class, and we are also specifying air class on connector pipe and air porous A class on three different legs. Also we are specifying these 2D classes, and for meshing we are specifying for mesh attributes we are specifying size A and size B class. So if we check the schematic. So this is how it look like: inlet, outlet, fluid, air porous A, and size A, size B, and BL wire A. So this is how the schematic looks like. As there is no rotating part, so on this viaduct model we are not specifying or tagging air rotate A class. So this is graded out. So now copy the required data from CAENexus installation directory. So I am copying this folder to this location, and I am from scratch folder. I am using this Accusol 17 basic menu to 1 AMF, and I will be using already tagged CAD models. Start the fluid nexus with appropriate CAD modeler. So CAENexus window is open. Now set the working directory. So I am setting up the working directory to the scratch folder. Now open this basic menu to one AMF file and save as this file as viaduct underscore accusol 17. Now import the CAD model. So I am importing this viaduct CAD model. So you can see that there is blue tick mark on the classes which are imported. So on air rotate A there is no tick mark, so this class is will not take part in this abstract model process. So now check the meshing attributes or boundary layer attributes. So on size A we have specified the 6 mm mesh size, on size B 12 mm. Then we have already set up the boundary layer attribute, minimum curvature, mesh curvature. Now go to the problem definition. So here you can see that some relations are already created. This fluid inlet underscore 2D, R fluid outlet underscore 2D, and R BL wire A underscore no BL wire 2D. So these relations are already created. So if we check the simple boundary condition, so we will open this inlet inflow boundary condition, and as per our problem physics, point 1 is the mass flow rate. So the mass flow rate is specified. Pressure outlet boundary condition is also specified, and as there is no air rotate class present in the CAD, so this is not enabled. And you can check in element set attribute. So air porous A class is attached on these three legs. So and material is air porous A, and inside this material model we have specified or selected the porosity model. So now there are only three simple steps, that is create simulation model, and you can check in model tab how attributes are transferred. So here the mesh size attribute is transferred as size A is attached on connector pipe. So 6 mm mesh size is transferred to connector pipe. Also inside cell zone attributes you can check all these three legs are having air porous A class. So porosity as element set attribute is specified or transferred, and as air class is attached on connector pipe, so on region 1 element set attribute is transferred. So you can also check the inlet boundary condition. You can also check inlet boundary condition and outflow boundary condition. Now next step is to mesh the model and export it. So meshing is completed. You can check. You can take a cut plane to check the boundary layers or meshings. So I am hiding remaining. So you can check here that the boundary layers are generated and 6 mm size is the fine mesh size is on this connector pipe, and on porous zone there is 12 mm size. Now next step is export the job and run the simulation. Now have a look at our product description and schematic of our abstract model for white tube. So here there are two inlets. We are having mass flow rate of zero point 0.1 kg per second, and this is the schematic, and here are the classes attached. These are the 2D classes, these are the 3D classes, and this is the schematic. It is similar to somewhat similar to viaduct model. So now again start the fluid nexus and open the basic menu to an AMF file and import the geometry and check in model tab how the attributes are transferred, and mesh the model and export it and run the AccuSolve simulation. So this is how the results look like after completion of simulation. So now we will directly see the third model, that is MRF model. Have look at our product description and schematic of our abstract model below. So the mass flow rate is zero point 0.1 kg per second and pressure outlet boundary condition and rotating speed of 100 radian per second. So classes attached here are the 2D classes, then 3D classes. Here air porous A is graded out as it is not attached to this MRF model. Instead of air porous A, there will be a air rotate A class on rotating fluid. So this is the schematic. So inlet, outlet, fluid class, air rotate A class on rotating fluid, and air class on remaining components, size A, size B, BL bar A, and there are some global classes. The attributes are specified on these relations and classes. Now exit the previously open CAENexus and exit through CAD software. Now open a fresh CAENexus window and set the working directory to appropriate folder. I am setting it to MRF folder, and I am opening the basic menu to one abstract model file and importing the MRF pump CAD model. So here you can see that the air porous A is not active and it is not specified on CAD model. Instead, air rotate A is present. It is having blue tick mark as it is present in the CAD model. Similarly, the classes present in the CAD model are having blue tick mark. So some relations are created. So here, as per our problem description, there is a one inlet having mass flow rate of zero point 0.1 kg per second. So here the mass flow rate is 0.1 kg per second, and there is a reference frame rotating fluid which is having 100 radian per second rotating speed and it is rotating on z axis. So I am enabling this calculate rotation center. So this center is automatically, center value will automatically get calculated. Next, on rotate, boundary of rotate a class, the reference frame is selected, and also in element set the attribute is created on air rotate a class and this reference frame attribute is referred. So now create the simulation model, and in simulation model, in model tab, you can check how the attributes are transferred. So rotating wall, on rotating wall, the attribute is correctly transferred. Next, in element set, you can check that this is the rotating fluid. So on this attribute is transferred. So this is the inlet and this is the outlet. Now next step is mesh the model. Meshing is completed. So next step is export the job for simulation. So I am writing is at export underscore mrf. So I am exporting the job. Next step is run the simulation and check the results. So here this is how the results look like. This is a vector plot. So user can use this basic minute-to-one abstract model to start authoring their post-convection CFD problems. So thank you for watching this tutorial. See you in the next tutorial.